Howdy, students. Dan here. Just a few, kind of tips, hopefully, for your quiz. Just wanted to run through an example, might be kind of similar. Okay, so let's look at a function where we have a surface. So z is defined as a function of y and x. Here, my example is f of x equals y times x times the sine of x. Check. So from that, we could say compute the gradient. So should know how to do that. From that, we could then, let's say, C be the name of the level curve when we let z equal the point z naught. So we pick a height z naught, and then we just set that equal to that value. Notice that then z is not a variable anymore, so we could solve this for y, and we get y as a function of x. Conversely, a different way of doing it is, what if we just took the derivative of this, assuming that y was a function of x? Oh, sorry. So we have some kind of curve in space. We've got a curve. That's our curve C. And we're given a point, say AB, and we want to find the tangent line to that level curve at that point. So we need the slope of this. The slope of that is going to be dy by dx for that function, because now we've flattened it down to the xy plane. So y is seen as a function of x. Okay, so in order to figure out the equation of this line from this curve, we need to find the derivative dy dx, which we can actually just do implicitly for this. So derivative of this is a constant, so it's 0. Y becomes dy dx times the rest. So this is really just a big product rule. We get y left alone. Derivative of x is 1 times sine of x. Y times x times the derivative of sine is cosine. Whew, there's all of that. And turns out we could actually just solve that for our slope. And given any height z naught, we just plug that in here, and this will give us our dy dx for any x value. So if we plugged in an x value, we would then know the slope. Okay. Notice to get this formula, I actually plugged in what we know y is, because we had y here. It was easy enough to do that, but typically wouldn't need to. You could just leave that as y. Okay, so then we want this tangent line. We're going to give that a name. We'll call it L. Since it's in the xy plane, we could write its equation. Remember, point slope formula is y equals mx minus some x value plus some y value. So this is just plugging in the point A, B into these formulas. So in order to get my m, I plug AB, or just in this case a, because I simplified it to x. So we plug in an a for all the x's. X is our variable, minus a, and then this needs to be a b, which the b value actually comes from plugging in a to get y. So I actually simplified that and made it even more complicated, sort of, so that this is actually all just a function of some point a. So you tell me an x value a, and this will be the equation of the tangent line to the level curve at that x value. Okay, so one of the little fun things that we could actually check is that we could take this curve, and we could figure out a vector along that curve. And so that would be parameterized. We just let x essentially be our parameter t. And then because we don't care where it is, we want a vector that just points in this direction. This turns out to being just mt here. So we can just take this is our m for some a value, and we could plug it into this formula. So we have a particular x value equals a in this case. I plug that in, I get a vector. I have a gradient vector. We know the gradient should be perpendicular to a level curve. The tangent points in the same direction sort of as the level curve right at that spot. So those two should be orthogonal. So therefore, if I consider their dot product, that should be 0. We won't work through that entirely. But, next fun thing I could do is I could try to, say, classify all of the critical values of this. So we could take, and remember, a critical value is whenever fx equals fy equals 0. So we could figure that out for this function and set these equal. That's kind of a real pain. On another note, though, some of those might be saddle points. And if they end up being saddle points, we could go through the whole classification thing with the second derivative test. So we could figure out the second derivative. So here, notice in the gradient, we actually figured out the first derivative of, like, we figured out fx and fy. So taking the derivative of this with respect to x gives us that for fxx, and fyy, so notice x sine x has no y's in it. So if I take the derivative of that with respect to y, then I'm just going to get 0. And then the mixed derivative gives me a sine plus x cosine. Check. So then plugging that into D, where remember again the formula for d of x and y equals fxx fy. So this part fyy is just 0, so that's 0. And then minus fxy squared. Okay, so I only actually get 0, and then minus, and then this part here, I should write it in that part, is the fxy. So this is fxy. And we could figure out where that was always negative or positive and set values and classify them. So I hope that helps at least a little bit and makes it clear. Just to go through this really quick, we got a function that's defined as a surface. Don't forget how to take its gradient. We also can find a level curve by just setting it equal to a value. So if they give you like a point A, B, you just plug in, say, oh, I want the level curve when it's equal to, plugging in that point. And then we could also figure out, sometimes we can rewrite that function and we could take its derivative this way. Sometimes we want to do it implicitly. Sometimes that looks rather messy. Either way, we can keep going and write the equation of a tangent line. We can find a vector in the direction of that tangent line from that point. We can take its dot product. We should make sure that's 0. And then we could consider the critical points. And then we can use the second derivatives to classify the critical points if they're saddle points or other. Hope that helps. You will definitely need theorem 15.15 on the top of 986. Review that. Have a good one.